Foxtrot Delta, cleared for takeoff, 23 left, left turn when able, heading 150. Foxtrot Delta.
Some of the expenses of aircraft ownership are unavoidable facts of life. Others, like fuel and maintenance, vary from pilot to pilot and aircraft to aircraft, and are greatly affected by engine operating procedures. The purpose of engine management is to minimize the three variable costs associated with aircraft ownership: fuel, routine maintenance, and major overhaul or engine replacement. Engine management is practiced on the ground and in the air. Intelligent and informed engine operation will contribute to engine longevity. A thorough knowledge of engine systems and the principles of their operation will allow the pilot to respond quickly to unusual engine conditions. Sudden engine malfunction without warning is rare. More often, pilots can see trouble coming if they know what to look for. With the proper corrective action, the pilot can avoid costly engine problems. The cowl flaps, magneto switch, propeller pitch control, mixture control, and throttle provide the pilot with direct control over a number of variables. The traditional engine instruments, the tachometer, the manifold pressure gauge, the oil temperature and fuel flow gauges provide the bare essentials. But for precise engine management, they don't tell the complete story. Multi-probe EGT, CHT systems now augment the instrumentation of many aircraft.
I frankly think if you're flying seriously, no, I'm going to change that. If you as a pilot want to fly safely, as well as seriously, or even casually, you need the kind of probe that can give you this kind of information immediately. But it's a piece of equipment I wouldn't be without. As a matter of fact, I would not fly an internal combustion engine without a six-probe instrument. And
you don't have to have made numerous Atlantic crossings in a single-engine aircraft like Dr. Harmon to appreciate the benefits of modern engine monitoring. Safety, economy, and reliability are concerns of all pilots. Modern engine monitoring begins with exhaust gas temperature. Its relationship to mixture is the cornerstone of informed engine operation. Kaz Thomas, editor of Light Plane Maintenance.
The correct chemical ratio of fuel to air is called the stoichiometric ratio. And that's just a big fancy word for the fact that if you bring the fuel and the air together in exactly the right amount, you'll get the maximum heat and presumably the maximum work that you're looking for. There's a very simple way to know when you've achieved a stoichiometric fuel-air ratio, and that is you use your EGT gauge and you look and see where it peaks. And when you get peak EGT, you know that you're at stoichiometry. You're at the optimum fuel-air ratio. That's kind of the basic precept from which almost all other statements about leaning proceed, because all leaning is done relative to peak EGT.
EGTs produced by an aircraft engine running full rich are relatively low due to the cooling effect of excess fuel. As the mixture is leaned, the EGTs rise at first and then fall. The highest temperature or peak EGT occurs when the perfect balance of fuel and air has been achieved. At mixture settings leaner than peak, temperatures fall. Less fuel results in less thermal energy and lower EGTs. At higher altitudes where the air is thinner, peak EGT will be lower. At lower power settings, the same is true. Peak EGT is not a particular numeric temperature, but rather a relative, changeable value. For this reason, absolute numeric EGTs have no value for leaning purposes. For most aircraft, peak EGT corresponds to the most economical mixture setting. However, airframe manufacturers frequently recommend a mixture setting 25 or 50 degrees rich of peak. Some specify a mixture setting on the lean side of peak. The heart of any EGT system is the thermocouple probe, a junction of dissimilar metals which produces a small electrical current when heated. The probe is mounted in the exhaust stack, a few inches away from the exhaust valve. The temperature reported by this probe depends on its position in the stack. A location close to the exhaust valve will read a higher temperature. Further away will read lower. This makes absolute numeric EGT temperatures arbitrary and quite meaningless. Absolute EGT is an indication of the exhaust probe location and little else. But as we have already seen, relative EGTs like those which define the EGT mixture relationship are of great value to the pilot.
Heat's your main problem in any aircraft engine which is air-cooled, as well as water-cooled. Heat can kill a number of products, a number of parts I should say. It can kill the guides all the way down to the pistons and anything in between. Rings especially susceptible, and also the cylinder barrels. Heat is the worst part on the cylinder barrels. We've had an example where one overheated and it annealed the cylinder barrels as well as the rings, which means they became soft. They would no longer seal and they passed oil like you wouldn't believe. And all it takes is 5 or 10 seconds of overtemp on a cylinder and it's gone.
An engine's susceptibility to heat damage makes cylinder head temperature, or CHT, a second important component of engine monitoring. It is also measured by a thermocouple probe, of which there are several different designs. The bayonet or spring probe is mounted in a temperature well found in the cylinders of all modern aircraft engines. When the temperature well cannot be utilized, a gasket probe is placed under the spark plug to measure CHT. The adapter probe is yet another variation. It serves as a receptacle for a bayonet probe and also contains a thermocouple junction to measure CHT. Pilots may also encounter a fourth kind of probe. Unlike a thermocouple probe, a thermistor probe does not generate any electrical current. Instead, its electrical resistance varies with temperature, making it incompatible with thermocouple systems. Modern engine monitoring systems provide the simultaneous display of EGT and CHT for all cylinders. This information is the backbone of engine monitoring for normally aspirated aircraft. For turbocharged aircraft, there is a third important parameter: turbine inlet temperature.
I'd say that over 60% of the turbocharged engines that are delivered to our facility for routine overhaul and repair, we find turbocharger failures in the engine. There's also signs of turbocharger overheating, which is derived from the examination of the reciprocating parts and the combustion chamber and pistons in the aircraft engine.
From its position just upstream of the turbocharger, the TIT probe monitors the combined exhaust from all cylinders. Its temperature runs several hundred degrees hotter than any single EGT. The operational temperature of the turbocharger is greatly affected by power setting, mixture, and the wastegate. By controlling the amount of exhaust gas entering the turbocharger, the wastegate determines the amount of turbo boost delivered to the engine. Wastegates can be either automatically controlled, manually controlled, or fixed. An understanding of the principles of combustion and engine systems is the foundation of engine management. Ignition, timing, compression, mixture, and cooling have a direct effect on the combustion process. Any changes in combustion are reflected in the three engine temperatures. Thus, EGT, CHT, and TIT can be used to monitor the major engine systems as well as the combustion event itself. Testing the ignition system is part of the run-up procedure. While useful and often informative, the traditional mag check is hardly a thorough test. Let's take a closer look at this important engine system. Unlike a car ignition system, the magneto is a self-energizing device which converts rotational motion into a burst of electrical energy. The magneto is also responsible for ignition timing, which is adjusted by rotating the magneto on the engine block. Two independent ignition harnesses and two spark plugs in each cylinder complete the totally redundant ignition system. While total failure on this system is rare, degradation of any of the individual components such as the plugs, mags, harness, or P-leads can significantly affect both engine and avionics performance. Ignition is the foundation of the combustion event. Abnormalities in this system produce changes in EGT. During normal combustion, two plugs fire simultaneously. Two flame fronts move through the fuel-air mixture. With only one plug firing and only one flame front, the combustion process happens more slowly. There is less time for cooling of the exhaust gases before the exhaust stroke, and higher exhaust gas temperatures result. EGTs directly reflect combustion temperatures. However, EGTs are several hundred degrees lower. During the power stroke, the gases cool because of expansion and transfer of heat to the cylinder head and engine internals. This cooling of gases makes EGT an indirect indicator of engine timing. Late timing causes combustion to occur later in the combustion cycle. With less time for cooling, the exhaust gases are hotter on expulsion from the cylinder and produce higher EGTs. These principles of combustion find application in every mag check. The drop in RPM experienced during single mag operation is the result of the less efficient single plug, single flame front combustion. A uniform mag drop for both mags suggests that both sides of the ignition system are functioning identically, but this is not always so. Fortunately, EGT monitoring provides a more complete picture of ignition. For practical diagnostics during run-up, the simultaneous display of all EGTs is a necessity. The Graphic Engine Monitor, or GEM, uses a bar graph display to show EGT for all cylinders at once. Each column represents EGT for an individual cylinder. In the normal operating range, each illuminated bar represents 25 Fahrenheit degrees. Like a mercury thermometer, the columns rise with higher temperatures. CHT is indicated on the same display. The unilluminated bar in each column is interpreted as a pointer against the CHT scale on the right side of the instrument. The dark bar moves up and down to indicate higher and lower CHTs. The number 3 cylinder is now indicating 500 degrees CHT, well beyond the usual 460 degree red line. This GEM indication is typical of a run-up power setting. Switching to single mag operation causes EGT for all cylinders to rise evenly. If both sides of the ignition system are functioning properly, you will see the same uniform rise for both mags. Now we'll do another run-up and show how EGT will identify some common ignition-related problems. On the left mag, EGT rises more. In this case, late timing on the left mag is responsible for this indication. Here's another example. Switching to the left mag causes the loss of EGT in cylinder 3, indicating no combustion whatsoever. The right mag shows a similar indication on cylinder 6. In this situation, two similar problems balance each other and produce a uniform drop in RPM for both mags. Fortunately, EGTs give clear indications of a problem. A plug or lead on each mag is not functioning properly. These indications may be the result of a discontinuity in the ignition harness, a loose spark plug cap, a fouled plug, or a plug with a cracked insulator. Since the problem was balanced on both mags, the drop in RPM was uniform. Without simultaneous all-cylinder EGT indications, this elusive problem would have gone undetected. Takeoff is the most critical phase of flight. At full power settings, the engine undergoes the greatest stress and is most susceptible to malfunction. This makes proper mixture all the more critical.
At full power, your engine is set up very, very rich, super rich. And there's a reason for that. The reason is basically to keep the cylinders cool and provide some margin of protection against detonation or combustion knock, what we call pinging in an automobile. If the engine were to operate at, say, stoichiometric fuel-air mixture or the equivalent of peak EGT for takeoff, you probably wouldn't make it all the way through the takeoff roll. You'd probably encounter some type of abnormal combustion on the takeoff roll. And here I'm thinking of detonation primarily.
At full power, the EGT fuel flow relationship is radically different from that of cruise power. The high temperatures produced by lean operation can have serious consequences. Mike Flam, General Aviation Maintenance Technician of the Year.
We had one example where a pump failed, the engine-driven fuel pump, and she went lean just for a few seconds, and that annealed 6 cylinders, or it annealed 6 sets of rings in 6 separate cylinders, so it affected the whole engine. That's been one of the worst ones we've found from that type of indication.
Engine monitoring can often spell the difference between preventative maintenance and financial disaster. Victor Sloan, President of Victor Aviation.
My first experience with a multi-probe EGT CHT system was actually on the original test flight of our 24-karat gold Bonanza. And at that test flight at 5,000 feet, my technician that was along with me noticed a very high reading on the bars on the number 3 cylinder assembly. We came back and landed the airplane and discovered that one of the fuel injectors on the number 3 cylinder assembly had been clogged with a piece of foreign material, of which we did not feel in flight. That unit, having the multi-probe system installed in it, told us exactly in flight that something had gone in and obstructed the number 3 fuel injector on that engine on the first flight.
In many cases, a plugged injector or other fuel system anomaly will reveal itself during run-up. A mixture control check should produce an even rise and fall in EGTs. In this example, the number 2 cylinder responds differently to leaning. This is typical of a partially plugged injector.
Detonation's an interesting phenomenon because it's influenced by so many different things. I mean, fuel quality. Even if you as a pilot are minding your own business and doing everything correctly, all you have to do to get detonation is fuel up with avgas of the wrong octane quality or autogas of the wrong octane quality. Most of us have had that happen in our cars. So fuel, just the quality of the fuel by itself influences your detonation margin. But you can also influence your detonation margin by how you operate the mixture control. Basically, this is the reason that the manufacturers uniformly advise you not to lean to peak when you're above 75% power. because when you do that, you are favoring detonation. And detonation will make trash out of any engine and has made trash out of a lot of engines.
During normal combustion, the flame front moves smoothly through the fuel-air mixture. Under detonation, the fuel-air mixture explodes rather than burning like normal combustion.
Detonation is very difficult to detect because it's inaudible from the cockpit, and there really isn't a cockpit gauge that's going to automatically come on and show you detonation. The factory wired CHT, which just goes to one cylinder, probably isn't going to alert you to the fact that detonation is occurring. What you really need is as much information as you can possibly get. If you have EGT for all cylinders and CHT for all cylinders, and you can see them all at once, probably you will notice if one or two cylinders have started to detonate. The CHT will be abnormally high, EGT will probably be abnormally low. But you really have no chance of finding detonation without EGT.
In some cases, detonation can lead to a second form of abnormal combustion called pre-ignition. Pre-ignition occurs when temperatures inside the cylinder are hot enough to ignite the fuel-air mixture without the aid of a spark. Pre-ignition will elevate cylinder head temperatures even further and can result in the catastrophic failure of the engine in a matter of seconds. In spite of these dire consequences of a too lean mixture, the pilot should not be deterred from leaning. The design of the conventional aircraft engine makes leaning necessary.
At idle power, you also have some richness that maybe you don't always need. The only reason the engine is set up rich at idle power, and this mainly applies to carbureted engines, it doesn't so much apply to fuel-injected engines, but carbureted engines are quite rich at idle power, and the only reason for that is so that the engine will accelerate smoothly when you open the throttle. Quite frankly, you don't need to be that rich at idle power. When you're taxiing, you should be leaning.
Here in the Colorado Rockies, pilots of normally aspirated aircraft are often required to lean for takeoff to compensate for density altitude. This is easily done with the aid of EGT. A density altitude situation might produce EGT indications like these. The engine is leaned until EGTs resemble standard day indications. Turbocharged aircraft like the T-210 should never be leaned for takeoff or during any full power situation. Compensation for altitude is provided by the turbocharger in conjunction with the wastegate controller. As a normally aspirated aircraft climbs to higher altitudes, it experiences decreasing air densities, like the aircraft at a high-altitude airport. As the aircraft climbs, EGTs drop, reflecting a relatively richer mixture. By leaning to restore the EGTs to their original level, the pilot can maintain maximum climb performance to altitude. Turbocharged aircraft like the A-36TC require different techniques. In this type of turbocharger installation, manifold pressure is maintained through a wide range of operating altitudes. As the aircraft climbs, the wastegate closes to generate more turbo boost, and the manifold pressure remains constant. Leaning a turbocharged engine at full power will reduce detonation margins and could lead to serious engine damage. Even in the relatively undemanding cruise phase of flight, mixture management is important. Unfortunately, there is no single mixture management procedure applicable to all aircraft in all situations. Pilots seeking maximum fuel economy may be tempted to lean aggressively, but engine longevity is also a consideration. Generally speaking, leaner mixtures mean higher temperatures.
I think that Lycoming in one of its publications has said in black and white that they have found that TBO experience tends to be the best with cylinders that have been kept below 435 degrees on cylinder head temperature, which is quite a ways below their normal red line.
Airframe and engine manufacturers generally recommend mixture settings on the rich side of peak EGT of the leanest cylinder. Without a multi-probe EGT system, conservative leaning is the only prudent course of action.
Is whenever you think you have the proper fuel-air mixture, richen it some more, because when these engines are coming into our shop and we see the results of cylinders and turbocharged that have been running too hot, we're talking about spending a lot of additional money to make up for the damages that have occurred inside the engines.
Many pilots rely on a single probe EGT meter for leaning. The probe is mounted either at the collector of one exhaust bank or on the cylinder deemed leanest by the manufacturer. Unfortunately, fuel distribution is neither perfect nor constant. The leanest cylinder can change from flight to flight. Any fuel system anomaly can change the picture radically, causing one cylinder to run much leaner than the others. The Graphic Engine Monitor, developed in 1981, addresses this problem by displaying EGT for all cylinders simultaneously. Its microprocessor and sophisticated software took the technology one step further by providing a computer-assisted leaning feature. After establishing cruise altitude, the pilot will perform a course lean to within a gallon per hour of the intended fuel flow. Engine temperatures are allowed to stabilize for a minute or two before the final leaning procedure. The gem is placed in lean mode by depressing the reset button until the EGT annunciator begins flashing. The engine is leaned until one of the columns starts to blink. This annunciation identifies the first cylinder to reach peak. During leaning, the gem analyzes EGT information from all cylinders simultaneously and identifies the cylinder which reaches peak at the highest fuel flow. This is the leanest cylinder. Turbocharged aircraft should never be leaned such that TIT redline is exceeded. Many experienced pilots recommend very conservative leaning for turbocharged aircraft.
Personally, the way I would fly my airplane is to run the airplane at 100 degrees to 125 degrees rich or cooler from peak DIT temperature for safe, reliable operation. And I personally would not operate any hotter than that.
At low altitudes, where TIT redline is not a factor, peak can be found and used as a reference point for mixture setting. In a turbocharged engine, exhaust gas temperature is the result of a complex interaction of mixture, exhaust gas volume, and turbocharged manifold pressure. Any change in mixture setting alters the volume of exhaust gases. At leaner mixture settings, reduced exhaust gas volumes drive the turbocharger with less energy. This reduces the compression of the intake air and tends to contribute to a less energetic combustion process and lower exhaust gas temperatures. Because of these interactions, a turbocharged engine does not respond to mixture changes in the same smooth, linear fashion as a normally aspirated engine. When leaning a turbocharged engine, the initial coarse lean mixture adjustment should be followed by a much longer time period to allow for these interactions to reach equilibrium. Allow 5 minutes for engine temperatures to stabilize before leaning to peak. The turbocharger interactions also play a role when enriching the mixture after establishing peak. Enriching the mixture results in an increase in exhaust gas volume, which drives the turbocharger harder and increases manifold pressure. Higher manifold pressure results in higher EGT. This phenomenon is called turbo bootstrapping. When leaning to peak and enriching from peak, the EGT versus fuel flow curve assumes different shapes. A turbocharged engine's EGT will initially rise when enriched from peak rather than fall immediately like a normally aspirated engine. TIT is a function of how hard the turbocharger is working. At higher altitudes, the wastegate controller directs more exhaust through the turbo, and TITs run hotter. When TIT redline is exceeded, an enrichment of the mixture or throttle reduction is necessary to cool the exhaust gases and turbine inlet temperatures. After cruise power and mixture settings have been established, engine temperatures reach equilibrium. On the graphic engine monitor, EGTs and CHTs typically look like this. As long as altitude, power, or mixture settings remain constant, the display will remain unchanged. Like climb out and cruise, descent from altitude has its own mixture control procedures. Descending into denser air creates a leaner mixture. If the engine is operating on the rich side of peak, EGTs will rise as you descend. Fuel flow should be increased to maintain the same relative mixture. Enrich until EGTs assume their previous levels. When sudden power reductions and quick descents become necessary, pilots are concerned by relatively rapid changes in CHT, often referred to as shock cooling. Although it is frequently cited as a justification for engine monitoring equipment, shock cooling is a controversial subject.
I think shock cooling is played up much harder than it really is. Airplanes are designed to go high, go low, go full power at takeoff, go into Arctic areas, desert areas. The position of the cylinder assembly and the flow of air on the front cylinders of the engine is always an important point in shock cooling. Although if an engine is controlled and monitored very closely, those temperatures can be corrected for by good pilot technique. It's my experience from studying engines that shock cooling does not play as much of a critical role in catastrophic cylinder failure as does poor management of fuel-air mixtures in an aircraft.
We've had a few instances where people have shock cooled and actually blown cylinder heads off. But this has been a pilot problem. If they would have been watching the temperatures again, they could have seen that. This was just a factory-equipped airplane with a single CHT, no EGT, and they were doing practice engine failure.
Shock cooling is kind of like the UFO phenomenon. I mean, there's those people who believe in it, and there's people who say it doesn't exist. I think almost any engine expert would have to agree that certain operators, namely operators of jump planes and maybe glider tugs, are always having cylinder cracking, and it seems to be related to the way in which the engines are operated. In other words, if you grossly abuse an engine by operating alternately at full power and then chopping the power, I think any engine expert would say that's bad, number one. And number two, it probably can result in cylinder head cracks. But aside from that, having said that, the evidence for shock cooling and its effects is very scanty.
EGT technology is frequently thought of as a tool for extracting maximum performance and economy. The other side of engine monitoring is troubleshooting.
The fact that it gives you the pulse of your aircraft immediately. For example, I've had all kinds of experiences with this aircraft. There's 4,500 hours on this airframe. And I, frankly, from this point on, would never fly an airplane without a 6-probe unit. What it tells you is when there's some kind of a problem internal in that engine that you never can pick up by just listening to it.
The graphic engine monitor approaches engine diagnostics from a different perspective. The way in which the information is presented is as important as the information itself.
The GEM gives me a relative display so that I'm not really interested in exactly what the temperature is. But I know about where that temperature ought to be on my display, and that's what's important. Now, some people also...
The GEM owes much of its diagnostic capabilities to monitor mode. The heart of this technology is the computer chip. In this case, an Intel 8048 microprocessor. The GEM places itself in monitor mode automatically when the reset button is depressed after enunciation of peak EGT. In monitor mode, the GEM is constantly sampling, storing, and comparing exhaust gas temperatures. If any EGT should rise even momentarily by 50 degrees or more, the affected cylinder is enunciated. The column will continue to blink until the pilot hits the reset button. Monitor mode is an important diagnostic tool. It traps momentary or intermittent problems and alerts the pilot. These indications are valuable diagnostic information since they frequently foretell of a more serious permanent failure.
If I have an engine that's running rough, one of the first things I'll do is check both mags. And if it's a specific plug that's causing the problem, when I switch over to the left and or the right mag, I'll see an indication on which plug it is that's failed.
In this example, a fouled plug is found in the number 2 cylinder on the left mag. Even with something as simple as a bad plug, pointing your mechanic in the right direction can save you time, money, and frustration. With more serious problems, the savings are even greater. As with any instrumentation, its usefulness depends ultimately on the skill and knowledge of the user.
There's a real temptation among pilots to buy gadgets, expensive gadgets, and then put them in the airplane and expect them to pay for themselves immediately. I see that as a very real phenomenon, and unfortunately I think it's possible to put an EGT in your plane and get a little too aggressive with leaning right off the bat. What you should do is put an EGT in your plane for purposes of gathering information and getting to know your engine better. And just live with it for a while, not necessarily change your routine right away, but look at it, learn what you can about your engine from it, and then once you've gotten comfortable with the gauge, then go from there. But I think there's a temptation to throw an expensive piece of equipment in a plane and suddenly expect your life to be changed or have it rule you instead of the other way around. I think it's a matter of accommodating yourself to this new piece of gear and learning slowly what it has to offer.
The ability to detect early signs of impending engine problems and potentially dangerous engine temperature trends is an important safety feature. Mountain flyers in particular appreciate this aspect of engine monitoring.
We've picked up a exhaust stud failure where the stack came down about 1/2 inch, and we found melted aluminum from the fins heading towards the spark plug on the bottom of the cowling. This also was in an Aztec. All of a sudden the CHT went sky high right off the top of the scale because the flame from the loose stack was hitting the CHT probe. And that's what indicated, plus we had no EGT.
The ability to identify problems before they become serious failures is one of the major benefits of engine monitoring. Consider this indication which occurred during cruise in a normally aspirated Mooney at 10,000 feet. The pilot noted slight engine roughness coincidental with the annunciation. The GEM has identified a rise in EGT of 50 degrees in all cylinders. This uniform rise in EGT is similar to indications observed during the mag check. In fact, this indicates a mag failure. Hitting the reset button shows that EGTs have returned to normal, which suggests the problem is only a momentary misfire. If similar annunciations occur repeatedly, a full-blown mag failure may be on its way.
It's important to monitor trends. Everything that's important about EGT happens in terms of trends. And it's just a fact, if you ask me, that the way to monitor trends is with some kind of analog representation.
These are normal indications from a Continental IO 470 leaned for cruise. Over a period of 50 flying hours, there is a gradual trend towards poorer uniformity. Indications like this are most frequently the result of dirty injectors and plugs. Routine maintenance will restore the normal EGT pattern.
With a GEM engine monitor, an engine problem can be diagnosed in probably 1/3 of the time. Normally a gentleman comes in, I'll sit down, I'll talk to him, he'll describe what he's seen, heard, and felt. Vibrations, noises, mag drop, the whole works. Then I'll go out and I'll run the airplane, and I'll make my own diagnosis. If I have a GEM installed, I have 6 separate probes which will pick up any spark plug, ignition failure, or fuel failure, or anything in that area. That can cut down his time, his money, and my headaches. I don't have to spend 2 days changing spark plugs or cleaning nozzles or playing around with this and that, where I can just go out, diagnose it, okay, it's this ignition system, check 2 spark plugs, 2 leads, and usually I correct a problem that simple.
Even subtle variations in temperature like this rise in CHT can pinpoint problems. On the basis of this indication, a mechanic removed the cylinder and found a broken ring. Increased frictional heating of the cylinder caused the rise in CHT.
It's very common to have individual cylinder assembly failures which are completely separate from all the other cylinders in the engine. Basically, the number one problem is inconsistency in fuel-air mixtures as they enter the independent cylinder assemblies.
The simultaneous display of EGT for all cylinders is essential for easy recognition of fuel system problems. At full power, a lean cylinder can show an elevated EGT. At cruise power and mixture settings, EGT may be higher or lower depending on its position on the EGT curve. Each example of engine diagnostics presented here depends on a combination of data from engine instrumentation, a knowledge of engine systems, flight conditions, and the application of logic. Unfortunately, there are too many variables for a simple cookbook approach to engine diagnosis. By the same token, engine management is not a matter of operating your aircraft according to set procedures, but rather adapting your flying technique to your particular needs, the limitations of your aircraft, and the situation at hand. Performance, economy, increased engine life, preventative maintenance, and reduced maintenance costs. These are the benefits of intelligent engine management. In each case, information is the key. Supplying this information is the role of truly sophisticated engine monitoring systems. Advances in technology are putting you in command of your aircraft like never before. Because with the right information, you'll do a better job. And that's what it's all about.